Welcome to ZT online course. I'm the lecturer of this course, Zhang Dong. This course is LTE Key Technologies. Okay, let's see the contents of this course. From this course, we'll study OFDMA technology, MIMO technology, high order modulation technology, and HARQ technology. Okay, let's see the first one, OFDMA technology. First, we need to know why using OFDMA in LTE network. And here we can see why using OFDM. Actually, OFDM and OFDMA, they are different. So what's the relation between OFDM and OFDMA? We can think OFDMA equal to OFDM plus TDMA. Okay, so actually LTE we are using two technologies, OFDM technology plus TDMA technology. And the TDMA is very similar, it's similar like before, right? TDM is time division multiple access technology. So now we just talk about OFDM. OFDM means orthogonal frequency division multiplexing. So so here we need to know what's the difference between OFDM and FDM, because we know in 2G we are using FDM, right? But here we are using OFDM. So in FDM we can see different carrier. This just like different carrier. They are divided. They cannot close, right? And also they cannot overlap. Why? Because if they are close or they have wide, they are overlapped. Maybe there has interference. But in LTE network, you can see the neighbor carriers can overlap. Why they can overlap? Because of orthogonal. So what is orthogonal? Orthogonal just like, for example, I will give you one example. If one people speak Chinese, another people speak English, we can think these two language is orthogonal. Orthogonal just means no relation. It's similar like 3G. 3G we are using orthogonal code, right? Orthogonal code. So that means code A and code B, they are orthogonal. So if they are multiplying, the result is 0, is nothing. So in here is the same. In LTE network, the neighbor carriers, they are orthogonal. So this carrier and this carrier overlapped is nothing. So that's why they can overlap. Only orthogonal, they will not interference. So it can overlap. So after overlapped, we can see it can save resource, right? Because our resource can be fully reused. Okay, fully reused. So this is the FDM and OFDM comparison. And the next here, the bandwidth your utilization rate is higher than FDM. Yeah, of course, because here we can overlap. And the next, the frequency selective fading is small and the time selective fading is small. Why this two fading is small? Because we know in previous network, if the frequency interval bigger or the time interval bigger, they all very easily cause frequency selective fading and time selective fading. But in LTE network, we can see the subcarrier, the carrier interval is very short, is almost 15 kHz. And also in time unit, that interval also is very, very small. So we think if the frequency interval and time interval is small, that means the fading also will be small. Okay, fading also will be small. Just like what, for example, if you play piano, if you play do, re, mi, re, do. So that means if between do and re interval is very big, I think you will be very easily to listen. The sound is increase or decrease. Do, re, mi, re, do, right? But if I play piano if I play these three very short interval, for example, do, mi, mi, do, maybe you are very hard to find the sound is increase or decrease. So in here it's the same. If the frequency interval is very short or the time interval is very short, you will very hard to find signal fading. So that's why we said in OFDM system, the frequency selective fading is small and time selective fading. Okay, next we can see the principle of OFDMA. We can see there has two pictures. The first one is downlink. Okay, this is downlink. The second one is uplink. So in LTE downlink, we are using OFDMA. But in LTE uplink, we cannot use OFDMA. In uplink, we are using SC-FDMA. Why in uplink we cannot use SC-FDMA? Because OFDMA has a big problem is PAPR, peak average power ratio. And as we know, in uplink, the transmitter is UE, right? And the UE, we are using the battery. So we want to save the power. So in uplink, we are using the SC-FDMA. Okay, this later we will introduce. Now we can see downlink. Downlink, we still use OFDMA because downlink is our base station, our site transmit. The UE just receive, right? Okay, so we can see the in downlink OFDMA procedure. So that means here is our base station. Okay, base station now want to transmit some information to the UE. How to transmit? Because we will transmit our information in air interface, and air interface is open interface. So before we transmit, we need some process. For example, before we transmit, we need channel coding, we need interleaving, and we need scrambling, right? Those technologies, they all can help to overcome some interference in air interface transmission. For example, channel coding. Channel coding is like we can add some redundancy bit to help you to correct some discontinuous errors. And interleaving is like change transmission sequence. It can help you to overcome some continuous errors. Okay. After that is modulation. Okay, modulation. And LTE modulation, we can support QPSK, 16-com or 64-com. So different modulation is based on the environment. That means if your environment is good, you can choose 64-com modulation. If the environment is not good, you only can choose QPSK. Of course, the high order modulation, it can give you high data rate. Okay? And also, after modulation, we can change our bit rate to symbol rate. So before modulation, here is our bit. After modulation is our symbol. So through the modulation, we can find a relation between bit and symbol. For example, QPSK. QPSK here means 2 bit per symbol. 16-com means 4 bit per symbol. 64-com means 6 bit per symbol. Okay, no problem. So after modulation, we can change the bit to symbol. After that, okay, this blue part is OFDMA. Okay, we can see OFDMA how to process. And we can see no matter channel coding, interleaving, scrambling, or modulation, our signal is still what? Is a serial signal, right? Our original signal is a serial signal. But if you want to use the OFDMA, we don't want to transmit serial signal. So the first step is the serial to parallel. Okay, serial you can think just like we will transmit one by one by time, right? Parallel signal just like we will transmit by the frequency. Okay, so this procedure we can also think just like time domain change to frequency domain. Okay, frequency domain. So we want to transmit our information in different, in the wide band, okay, in wide band. So this is serial to parallel. After that is a subcarrier mapping, okay, subcarrier mapping. And here, the subcarrier you should know in LTE, in frequency domain. For example, if your bandwidth is 20 megahertz, right? 20 megahertz only can use 18 megahertz, okay? And 18 megahertz we will divide by several subcarriers, and each subcarrier is 15k hertz. So you can use 18 megahertz divide 15k hertz. The result is the number of total subcarriers. I think that result is 1,200. And each subcarrier is just like one resource. Actually, our data, it will transmit by each subcarrier. But how many bits can be transmitted by subcarrier is based on the modulation. For example, if your modulation is QPSK, that means each subcarrier only transmit 2 bits. If you use a 16 QAM, that means each subcarrier can transmit 4 bits. If you use a 64 QAM, that means each subcarrier can transmit 6 bits. Okay, so this is more. So after subcarrier mapping, that means, okay, we will set different bits to different subcarriers. For example, if now I want to transmit 8 bits, okay, and I use QPSK. Okay, so we can use 8 divided 2. The result is 4. So that means in this case, we need 4 subcarrier mapping, right? 4 subcarrier mapping. Okay, and then the next step is IFFT. IFFT. So first, we should know what is FT. FT means Fourier transformation. Okay, Fourier transformation. And FFT means fast Fourier transformation. Fast Fourier transformation. I means inverse Fourier transformation. So what's the function of here? Here, IFFT just change time, just use for change frequency domain signal to time domain signal. Because finally, our signal will transmit by antenna, right? Our antenna only can support the time domain signal. So here is the frequency signal, so cannot transmit by antenna. So we need the IFFT to change. So after IFFT, our signal will change to time domain again. So after IFFT, here is time domain, but here before serial to parallel, this also time domain signal. So why we need to do these two procedures? Because this time domain signal is different with this time domain signal. This time domain signal is original signal, right? Only time domain signal. But this time, after IFFT time domain signal, actually this signal includes so many frequency information. Okay, so many frequency information. But after IFFT, our signal cannot transmit directly. We need what? We need to add CP. CP is a cyclic prefix. Cyclic prefix. Why? Because if we are not add CP, if we transmit our signal, it will have two different interference. The first is intersymbol interference. The second is intercarrier interference. So after add CP, we can avoid intersymbol interference and intercarrier interference, and then you can transmit. Okay, so this is downlink OFDMA. We can see uplink. Uplink, this procedure is the same like downlink. And also subcarrier mapping, IFFT and CP is also same. Just here is different. Okay, so that means in uplink we will add one more step, is DFT. DFT means discrete. Here, discrete Fourier transformation. Actually, This technology full name is DFT-SOFDMA. S means spread, okay? It's a spread. Spread is like we can change our narrowband signal to wideband signal, okay? So wideband signal, it will not have PAPR because the narrowband signal, because here is so many 15K hertz narrowband signal combined to one time domain signal, right? So in this case, we will have PAPR, but in this procedure, because of their wideband signal, so even we combine no PAPR. So that's why in uplink we are using SC FDMA can lower the PAPR. Okay, so we can see this is the OFDMA and SC FDMA. We can see in this example we are using 2 PSK. That means each color you can think just like one symbol. Each symbol can carry 2 bit, 2 bit, 2 bit, 2 bit, 2 bit. Okay, and in downlink you can see each 15K hertz 2 bit, 2 bit, 2 bit, 2 bit, right? 2 bit, and each symbol length is one symbol length, right? One symbol length. Okay, 4, 4, and we can see uplink. Uplink we can see first we will spread 15K hertz to 60K hertz. So this is wideband, right? And as we know, the bandwidth increase. That means the time it will be reduced. Okay, time will be reduced. So we can see in uplink, still 4 symbols, 8 bits. We also just like one by one to transmit, right? So after you use SC-FDMA, this is just like a wideband serial signal, right? This is a wideband serial signal. So wideband serial signal, even you combine, still one signal, right? So there's no PAPR. Okay, so this is a OFDMA and SC-FDMA. Okay, the next technology is MIMO. So what is MIMO technology? First, we can see the MIMO categories. The MIMO has, actually, we have a CISO, CMO, and a MIMO, right? CISO is a single input, single output, just like this. Single input, single output. One antenna transmit, one antenna receive. This mode is not reliable, right? If the distance increase, I think because only one transmit, right? So this is not good. Okay, the second is CMO or MISO, right? So this is a transmit diversity. This is receive diversity. Okay, so use this or this. It can improve the coverage because now we are not only one antenna receive, right? We have 2 antenna receive. Even the first antenna receive fail, we still have the second one, right? So this compared with the CISO, it's better. Okay, what is MIMO? MIMO means multiple input and multiple output. That means transmitter and the receiver, they are all using multiple antennas, right? So at least 2 antennas, right? So in here, the transmitter, 2 antennas, and the receiver, 2 antennas. And the red color and the blue color represent the same information, okay? So we can see, in here, we can see this antenna. This antenna can receive the red color signal, and this antenna also can receive red color signal, right? So this just like diversity. And also, this antenna can receive blue color signal. This antenna can receive blue color signal, also like diversity. And also we can see this antenna can receive red and the blue signal together at the same time, right? So what's this? This is not diversity. This is a multiplexing. So what's the difference between MIMO and CMO, MISO, and CISO? MIMO has multiplexing plus diversity. Okay, so that's why in LTE we are using MIMO, because diversity can improve the coverage. Multiplexing can improve the data rate. So MIMO can realize these 2 functions together. Okay, so LTE we are using MIMO. And LTE basic MIMO configuration has a downlink 2x2, uplink 1x2, maximum 4x4. That means in LTE we can use the maximum 4x4. But in uplink, we cannot support MIMO, right? Because uplink, the terminal only one antenna transmit. Okay. LTE terminal only one antenna transmit, so cannot support MIMO. But LTE terminal has a two antenna receive. So in downlink, we can support MIMO. Okay. Next, we can see the MIMO mode in release 9. Okay, 2009 release. So this is a 3GPP defined 8 mode of MIMO. So that means during the configuration, we can select which mode we used. Okay, the first mode, mode 1, is what? The mode 1 you can think is a single antenna port, right? So this just like what? This just like CISO. Okay, the mode 1 just like CISO, single input and single output. Now we are not use this one. Okay, the second one is transmit diversity. Transmit diversity, it can improve the downlink signal SNR. Diversity just, so that means the two antennas, right? For example, you have two antennas transmit, but these two antennas, they are transmit the same information. Because the same information transmit together, this is diversity, right? So this mode only can improve the coverage. For your throughput, for your data rate, no effect. Okay, how to improve your data rate? How to improve your throughput? We are using mode 3 and mode 4. Mode 3 and mode 4, they are multiplexing. Okay, so because of multiplexing, it can improve user peak rate. But we can see mode 3 is open loop. Mode 4 is closed loop. What's the difference? Open loop, you can think just like no feedback multiplexing. Closed loop is a feedback multiplexing. Okay? And in which case we are using mode 3 and in which case we are using mode 4. I also can tell you for high speed scenario we are using mode 3. For normal speed, for low speed scenario we are using closed loop. Okay, so mode 3 is for high speed scenario, mode 4 is for low speed scenario. Okay, mode 5 is a multi-user MIMO. Multi-user MIMO, it can improve the sales throughput. So here, please pay attention. This not improve the user throughput, right? This can improve the sales throughput. So the sales throughput, you can think it can improve the sales capacity. So that means we can support more users. Okay, more users. Normally, we can also use a multi-user MIMO in uplink, right? Uplink. Okay, next, mode 6, 7, and 8. They are all using like a beamforming. Okay, beamforming, this is another technology to improve the coverage. Okay, so they all can improve the cell coverage. So in here, you should pay attention mode 2, mode 3, and mode 4 because in real network, we are widely used these three modes. So that means if you just want to improve the coverage, okay, please select mode 2. If you want to increase the throughput in high-speed scenario, please select mode 3. If you want to improve the throughput in low-speed scenario, please select mode 4. Okay, mode 4. And mode 1, we are not choose because mode 1 is a CISO. Okay, this is not reliable. Okay, and mode 5 is for multi-user MIMO. It can improve the system capacity. It can improve the cell capacity. Okay, so this is a LTE downlink MIMO mode. Okay, the next, let's see about high order modulation technology. So this is the modulation in LTE. And LTE we have BPSK, QPSK, 16-QAM, and 64-QAM modulation. And high order modulation can improve the peak rate, right? For example, BPSK. BPSK, that means one bit, one symbol. QPSK, 2-bit one symbol. 60-com is a 4-bit one symbol. 64-com is a 6-bit one symbol. So that means the same symbol, but it can carry different bit. Of course, same symbol, the more bit, that means your throughput is more fast. Why? Because the symbol rate, they're all the same, right? So the same symbol rate, if you can carry the more bits, of course, your data rate, it will be higher, okay? And here, different type of bit, how to represent, for example, BPSK and QPSK, we are all using face to distinguish different bit, right? For example, in QPSK, 2-bit per symbol. 2-bit, of course, there is a 4 different case, right? 2-bit may be 00, maybe 01, maybe 10, maybe 11. So how to represent these 4 symbols? Well, okay, we can base on different phase. This is phase 1, phase 2, phase 3, and phase 4. And the 16-com and the 64-com, we can see there's a 4-bit per symbol, right? 4-bit per symbol totally has 16 different types. So in this case, only use phase is not enough. So here is a phase plus amplitude represent, okay? And the 64-com is also, we are using phase plus amplitude. So we can see in 16-com modulation, each phase, you can see this phase, each phase has 4 symbols, right? 4 symbols. And the different symbol, there's a different degree and different amplitude. And here, also, there's 4 phases, and each phase has 16 symbols, right? And also different symbols has a different degree and a different amplitude. Okay, so this is the high order modulation. So you should remember the high order modulation can help improve the peak rate. Okay, the last technology is HARQ technology. So what is HARQ? Before we learn HARQ, we need to know what is FEC, what is ARQ. FEC means forward error correction. ARQ means automatic repeat request. So they also just like 2 technology. So what is forward error correction? Just like if you send the data to me, okay, first I will do the FEC coding. FEC coding just means this technology, it can correct some errors. I can try to correct errors, okay? And after that decoding, you can receive data, right? I can correct. But this technology has a problem is because not all the errors can be correct, right? So if you use this technology, some errors cannot correct, maybe the receiver cannot receive this signaling, cannot receive this information, right? Okay. What about the second technology? ARQ. ARQ is automatic repeat request. So that means this technology is like if you send the data to me, I just check this data has error or not. If no error, okay, I will feedback ACK I received. If it has error, I will feedback NACK, non-acknowledge. Okay, non-acknowledge. So this technology cannot correct error, but it can feedback. But this technology can correct error, but cannot feedback. So what is HARQ? HARQ just like we will add these 2 technologies together. So during the data transmission, first we will use MEC, try to best to correct error, right? If I can correct error, everything is fine. I will feedback ACK. If I cannot feedback, if I cannot correct error, I will use the ARQ technology, feedback, right? Feedback to the transmitter. Please transmit to me again. Please retransmit, right? So we can see in HARQ, ARQ has high reliability, but FEC has high efficiency, right? Because FEC, it can correct errors by itself, but ARQ, it can feedback on time. So in ARQ, we are using these two technologies together can help our data transmission reliability. Okay, reliability and efficiency. We want our data transmit, it can be more reliability and more fast, right? So we are using these two technology together. We named HARQ. Okay, so this is the end of this course. Thanks for your learning.